Welcome. In this talk, I will introduce Git as a version control system and explain its role in enabling open science. Version control has been developed since the 1970s as a fundamental technology in software development. It's applicable to any body of knowledge that's built up incrementally and involves multiple collaborators. While originally for software, it naturally extends to data and science publications as well. Version control backs up changing files, keeps a history of those changes with detailed log messages, and facilitates merging those from multiple authors. If you have directories that look like this screenshot from the PhD comic, then perhaps you should be considering a version control system. In open science, transparency and reproducibility are important values which are byproducts of using a version control system. It enables collaboration between colleagues. Importantly, it also allows collaboration between yourself when using multiple computers. Working as a time machine for your projects, it gives you the power to track blame and/or praise and removes the fear of breaking things. In publications about open and reproducible science, reference is often made to the importance of version control for sharing data, code, and publications. We can compare version control to Google Drive or Dropbox, where there are shared files, or a track changes feature in an application like Microsoft Word. Traditional version control systems start with a base document and then record the changes made in discrete steps. Think of it as a tape. If you rewind the tape and start at the base document, then you can play back each change and end up with your latest version. If the changes are separate from the document itself, you can then think about playing back different sets of changes onto the base document and getting different versions of the document. The older version is just playing back one change. The newer version is playing back the second change. This allows two authors to make independent sets of changes on the same document. A common example might be you editing a file on a laptop and then also on your desktop office computer. Which copy of the file is the new one? Well, of course, they both are new. Yet, version control solves the problem of handling the merging of those changes back together. There are other version control systems available, but at the moment, Git is incredibly popular, especially in open science. Unlike many traditional version control systems, Git tracks snapshots of a whole file system. It is not just a new version of each file that's being tracked, but the entire collection of files altogether. In Git, each snapshot is called a commit. Services like GitHub make it easier to organize relationships between repositories, but a central server is not actually required with Git. We say Git is a distributed version control system where there's no one special copy of the data. Every computer's repository has a complete copy of the entire history of all the data. Its technical design makes it very fast even for very large projects with thousands of different contributors. However, as suggested by this XKCD comic, Git sometimes has a reputation of being cryptic and mysterious. My hope is this presentation provides some insight. Front-end tools for working with Git include the command line or desktop applications such as GitHub Desktop. A quick note on GitHub and how that's different from Git. GitHub supports much more than just version control. It also includes development tools such as issue tracking, project management and collaboration tools, and continuous integration, continuous development features. Learning what the commands actually do by using a lower-level tool like a command line is great for understanding. For productivity, using tools built into your favorite applications may be better. For example, I do much of my day-to-day work using the editor Visual Studio Code. There are plugins and extensions that allow me to add and commit changes with Git right from within that editor. While not a perfect analogy, recall learning elementary school math. We learned how to do things by hand to understand what was going on, but in practice, we can use a calculator. There is value in learning Git with the command line. Here is the overall Git workflow. These are the command line versions of the steps, but any graphical client will be doing these same tasks. We start by getting a copy of the repository. Assuming we are continuing an existing project, this is called cloning. Git is a distributed version control system, so cloning means making a copy locally of both the current version of the files and the complete history of all the commits. That is the historical version of all the files. Git has commands like status and log that are able to review the repository of the project, see the changes that were made, who made them, and when. Once you've made some changes, you commit those changes to the repository. Each commit is a reference with a hash or code that uniquely identifies it and what the commit is based off of. Well, not exactly equivalent. A Git commit history shares similar elements to a blockchain that you might have heard about related to cryptocurrencies or NFTs. A commit in Git represents a file system tree with a number of files, sometimes called blobs or objects. Commits are linked together to form a repository, and it's this repository that's replicated when it's cloned. References to those hashes are how Git distinguishes different versions of files. The head ID or pointer is an alias for the most recent committed hash. In Git, we sometimes talk about a branch. A branch is just a reference to another commit that's not the head. As such, branches, being just references, are incredibly cheap to make within the Git framework. Commits also require the use of log messages. Log messages are very useful if used properly. They help other people, your colleagues or your future self, to understand the intentions of each commit. A good commit message captures the intentions of a commit and provides some context. Finally, you can fetch changes from someone else's repository and merge those changes into your repository. Together, a fetch and a merge is called a pull. To share changes from your repository to someone else's, you push those changes. Now, there's really nothing special from Git's point of view about the server. Git doesn't need a central repository since it's a fully distributed system. However, to communicate those new changes, services like GitHub are often used as part of the Git ecosystem. This communication has led to the growth of online communities such as the Pangeo project. And being able to participate in those communities where open ocean science is being done is a strong incentive to take the time to learn how to use Git. When using GitHub, we also need to introduce two new concepts, forking and pull requests. A fork is a copy of a repository that you manage. Forks let you make changes to a project without affecting the original repository. You can fetch updates from or submit changes to the original repository with pull requests. Pull requests let you tell others about changes you've pushed to a branch in a repository on GitHub. Once a pull request is opened, you can discuss and review the potential changes with collaborators and add follow-up commits before changes are merged to the base branch. GitHub supports pushing directly to a repository as well, but with pull requests, you can allow anyone to contribute to a project without them first having to be a trusted party. A pull request, or PR, is just that. It's a request that a repository maintainer will make a Git pull from a previously forked repository. As a way to experience Git and GitHub, we've designed a short tutorial for the second part of this session. I'm looking forward to you joining us. Thank you.